When we looked at what a wave is, we talked about the energy within a wave. As one point moves, it drags another point along with it, and so thus pushes some of its energy forward to the next points in the wave, propagating all along down the line. Let's take another closer look at energy within waves. So you have a wave. If we can get that wave to spread out three-dimensionally from some source, so it radiates outwards here in some spherical shape, then the energy from that wave has to spread out so that it covers the entire wave. Here's what I mean. Here we've got our initial wave. We're just looking at this segment of the sphere here. As that wave moves out, notice what happens to the length of my line, of my arc. My arc is definitely much longer. It has the same amount of energy, but that energy has to be spread over a much larger area. Likewise, when we get out here to the outer side of the sphere that's drawn, it's an even larger area. The energy, the same amount of energy has to be spread out through that whole area. Now, we're going to go back and forth between energy and power, so I want to remind you, power is equal to energy per unit time. In other words, power is how much energy is used or transmitted in a given amount of time. Okay. Now, here's a very important point. If you look at the amount of power in the wave when it reaches a radius of r1, and you look at the amount of power when it reaches a radius of r2, well, the wave is moving at the same velocity. The velocity hasn't changed at all, and the amount of energy is the same for both points. It's just that the energy is more spread out at r2. So that means the amount of energy is the same at both points, and the speed at which it passes by is the same. Therefore, the time is the same. That means that energy divided by time, or power, is the same at both points. Now, that's an important point that will come back in a couple of slides. So the energy is constant, but it is spread out across the area. So we are going to actually measure energy and power not as individual energy and power, but in terms of intensity. So the intensity is the amount of power divided by the area over which the power is distributed. So power divided by area. Okay. So we may just simply write this as I equals P over A. Now, down here at the bottom of the slide, I'm going to mention this. I'm not going to give you any equations on it, but it's something to remember. The intensity, here, let's do this in a different color just so we don't confuse ourselves. The intensity is also proportional to the square of the amplitude of the wave. So if you have a certain intensity, you have a certain amplitude. But what happens if you double the amplitude? Well, if you double the amplitude, that double is squared, which means you increase the intensity by a factor of 4. So that's an important point to note. But this deals with amplitude, not area. It's kind of confusing because they both use the same letter, but I just need that to be clear. Okay. So intensity is equal to power divided by area. And area, let me come back and get my red pen again. Area for a sphere is calculated as 4/3 pi r, cubed. This is the volume of a sphere. I apologize, I got ahead of myself. The area of a sphere would be 4 pi r squared. There it is. And since the intensity is equal to power divided by the area, then that means that the intensity is inversely proportional to the square of the radius. Meaning, if I double my radius, then what happens to my intensity? It gets cut by a factor of a fourth. So 1/4 of the intensity would be proportional to 1 over the doubled radius squared. So that's an important relationship to note as well. In fact, we can get better than this. Remember what we said a couple slides ago, that the power at point 1 is equal to the power at point 2. Well, intensity equals power divided by area, so power then is equal to intensity times area. And so that tells us that the product, intensity times area, is equal for both points as well. Well, how do we calculate area? It's intensity times 4 pi r squared on both sides. I neglected the 4 in this equation, but it doesn't matter. The 4's will cancel out anyway, but yes, that 4 should be there. So the 4 pi on both sides cancels, and you're left with an interesting relationship, that the product of the intensity with the square of the radius is a constant. And so, as a result, if you know the intensity here, then you can easily find your intensity at any other point.